Hello again. Thanks for joining us here in Luzhniki Hack Days in the Orion Hall. We will have a presentation about Polars and PyArrow. Who is using Apache Spark and who would like to use it, do it without it, with the same speed? So we don't want to use Java, and Vladislav will speak about Polars and PyArrow. Please use our bot to send questions and to evaluate the presentation, because it's very important for us, organizers, and for the speaker. Vladislav, over to you. Hello, everyone. I am going to speak about industrial use of Polars and PyArrow for big data. I will speak about how we can do it with the limited resources and without the use of Spark. Let me introduce myself. I'm Vladislav, head of data research in Sberbank, in Sber. Last year, I joined the recommendation platform of Sber, where I specialize in development and creating product solutions for machine development. First of all, I will speak about the task. Then I will speak about the data I had to process. Then I'll speak about the limitations that I encountered and the potential solutions, how I'm going to fix this problem. And I will speak about the ultimate solution, about how I did it. I'll start with setting of the goal. First of all, we need to implement the machine learning solution on our recommended platform. What's the recommended platform? Recommendation platform, rather. It's made from a backend and front end, and ML tools are in the back end. ML tools, ML flow, and we have DS SDK written by our colleagues, which helps us work more conveniently with the components of the platform. We have integration of services and platforms based on Go and Python, and we have models and services that are generated by the users. With the UI part, the front part, we have iFlow, the orchestrator of tasks, and it allows you to check the status of whether they have been successfully resolved or not. And we have a web studio, studio web that allows you to configure these models. It helps you to come up with A/B tests and check the A/B tests results. I'm going to speak about the types of models that we use to promote the products. First of all, I'll start with the look-alike approach. The look-alike approach show the similarity. For example, we have a client, Vasya, with 100,000 rubles income and 2 children. And we have Petya with 2 children with the same salary, but without mortgage loan, unlike Vasya. So we may suppose that if we offer mortgage loan to this second guy, he is very likely to take the mortgage loan. Why do we need to use lookalike models? Because if we cannot offer something similar, if we don't have clients, VIP clients with too many communications, they don't like them, we use this lookalike approach. The second type approach is the response model. They show the probability of the response with communication. They send communication to some clients, and some of them agree, some don't. And this is the data used to base machine learning model upon. And the third one is the uplift model. These are the models that predict the probability of the target action with communication minus target action without communication. I will speak about it more in detail. So I had an uplift task. Uplift is the simulation approach where we can evaluate effect from client communication and select the most influential group. So we split the base of customers into two groups, control groups and target group. And we send communication to the target group, and we check their reaction, and we're doing nothing with the control group, just to measure the natural response to the product offered. So what are the groups of the customers? Like I mentioned, we need to find the most influential one. First of all, there's a type of customers that don't want to be disturbed at all. They hate each type of communication. The second group are lost customers, because with communication or without communication, they are disinterested, and that's it. The next group are loyal customers, are those customers that somehow or rather will buy your product. And the final group of customers are those that you can convince, those clients that if communication is provided, you can manage to talk them into your product. That's exactly the task, to find the customer that you can convince to buy your products. Of course, now I will speak about the data, like we are supposed to speak on data engineering track. I'll speak about which data I had to find and speak about the volume of the data, their size. First of all, I had to come up with the target. To come up with the target, I had to take three tables. First of all, the communication table, second of all, the table with the responses, and thirdly, a kind of a reference book, which would help me select the communication in an efficient way. And as far as size of the tables are, for communications, 145 million rows in one partition, for responses 3 million rows in partition, and for the reference book just 500,000 rows. And this is what these tables look like. The first table on the slide is the communication table, where we can see that there is a client, and here's the date of communication and the product, like, for example, a loan, a deposit. And the second type of data is client, the response date, product, and control group, whether the preliminary communication existed or not. I took these two tables and the reference book, and I ended up with something like this. I have a client, I have the response date, product, and the target event. One makes for yes, 0 makes for no. After the target event, I just need to add some attributes of the client to come up with a model. For this, I decided to use two tables that we have here. First of all, a table with some monthly aggregates and the table with some daily numbers. These tables had to be merged and joined by ID and data. Why would we have to join them with ID and data? Because if we develop this model in the month of May, and some client made that communication, made a response in February, and we'd join current data to that, we will have a data leak. So we'd receive data from the future, which cannot happen in the industrial scale. So we'd always join it by ID as well. Now I'll speak about the size of the tables. First of all, the monthly aggregates that had approximately 1,000 columns, and with only 12 of them really needed, and 200 million rows in a partition. With the daily numbers, just 100 rows, and it needed just 3, and it contained 200 million rows in one partition. These are the basic attributes of the client: its age, its income, and the date by which we will join the data. Ultimately, I end up with this kind of table where we have this target event, attributes like income, age, date, etc. After this, I can start the emulation. I'm showing the volumes of petitions here. With the biggest volume, I should mention the communication table. One petition had a size of 7 gigabytes. And altogether, for 6 months, I would have to get 185 such petitions. It resulted in 1.3 terabytes of data. The daily aggregates had approximately 8 gigs per petition. I needed 185 of them. Resulted in 1.5 terabyte. Altogether, the raw data volume was 3.3 terabytes. That's big data. Now, the development environment. In Sber, we have isolated access to data. That's where I did data mining. I came up with Spark, distributed Spark, with 2 cores, with 8 gigs of memory and dynamic allocation, with a maximum number of executors as 40. Altogether, I had approximately 320 gigs of RAM and approximately 80 CPUs. The time it took for data mining was 1.5 to 2 hours. After that data gathering and trying that model, we did conduct an A/B test, and that was a statistically valid model, and we would have to put it in production and use it. But the question arose about the limitations. The first limitation I saw is that I didn't have distributed Spark in PROM. I will elaborate on that later. The second limitation was having no disks in OpenShift. It was a demand, it was a strict requirement of the Information Security Department, and the maximum number of CPUs was 10 and RAM was 80. And there are other limitations for no distributed Spark. Spark can work in a distributed mode, sending the tasks to different nodes to process it all in parallel, but locally you just use one computer, one machine. So distributed Spark allows you to process more data in a shorter space of time. This is what it looks like on the slide. We have a Spark master, Spark driver, as it's called. It gives tasks to worker 1, worker 2, worker 3. These are the nodes, getting results from them. But I didn't have it. And another limitation, no disks in OpenShift. If Spark needs more resources than its RAM, it may start putting this data somewhere on a disk where it will spill this data. That is what it's called, spill. I couldn't use this spill because I had no such OpenShift disk, no such disks in OpenShift. So what could I do with those limitations taken into account? So I thought, what would be the methods applied here to the library? So here I understand immediately that nothing will happen with these limitations, so I had to come up with something else. What? So I thought about PyArrow, I thought about Polars and DuckDB. I will start with PyArrow. We'll speak about details, advantages and disadvantages, and interesting features. PyArrow, Apache Arrow, in other words, came up in 2016, and it was for more effectively and uniformly store data with the low-level API. As far as efficiency and performance is concerned, it's great and cool, but if Spark exchanges data between the driver and Python code, they do it in the Arrow format. Arrow is used in Polars and DuckDB, and starting from the 2.0 version, we started having it as well. What are the advantages and disadvantages of PyArrow? The main thing is very high speed, very high speed, low utilization of random access memory, then support of different sources and formats, and support of different file systems. It can work with local file systems and cloud systems. As far as minuses go, Arrow has a low-level API. It has a limited set of functions and complex syntax. It has data schemas. If you take a look at Sparks and casts, you just go there and cast it. And here, for the entire table, you just need to come up with the schema for all of the attributes. It's a Python interface to work with Arrow, PyArrow. That's what it stands for. PyArrow has a data set. It has functions for most effective work with very big data. When amount of data exceeds your resources, I mean, your RAM, for instance, with the push-down predicates, it can read the lines and strings with filters and do projections, the selection of columns, and read in parallel. I show it here in the table. For example, here's table A, which is partitioned by the partition field. We only need the last partition field, which dates to December the 31st, January the 31st, 2024. We need only the sum column. Call, that's one sum, and we need to read this data set to the memory. After we read it to the memory, we get this PyArrow table. With the PyArrow table, we can start work. The PyArrow table supports the joins, aggregations, more functions, in other words. Like I said before, PyArrow has a very difficult syntax. So I decided to check what else could be done, and I started checking Polars. First of all, what are the advantages of Polars? It was easy for us to move to Polars because the format they use, it's the same as Arrow. It's got much more functions, and it's much simpler and more convenient. If you need to have some groups, even if the speed is reduced, it's still very convenient, for me personally. As far as minuses go, it's slower than PyArrow, and it's got less capabilities than Pandas, and it's got fewer integrations with other libraries than Pandas. And if we take a classic data scientist, he more or less knows their solution, but Polars is going to be much more difficult for them to cope with. You have big volumes of data and you need to process them. In Polars, we have lazy API. Lazy API automatically optimizes the inquiry query and make sure that this query is processed in the most efficient way. For example, we have table A and table B, and we need to join them and filter them. With the non-lazy API, we come up with join and then add a filter, So it will go through the blue branch. So the tables first join, and then they are filtered. But if we use the lazy API and we did the same operation, then on the gathering phase, so when we collect it, it only then starts calculating this. So at the collect phase, it would understand that join is a very heavy operation. So it's best to filter the data first and then join the data, and then it would use the first scenario. Polars has streaming, API streaming. It's a part of the lazy API. When we call up the collect method from lazy API, we can send streaming equals true, and it will not calculate everything we ask for, but it will split it into parts. Like I showed it here on the slide, we can put it in different batches, run them consecutively, and we will get the same result. So we thought it would be a very good solution, but I started Googling the information, and it figured out that the GitHub says that the streaming uses some space as well, where they need to put this data, the intermediary data. So now I'm going to say a few words about DuckDB. DuckDB, what is it all about? DuckDB is an embedded relational database management system which appeared in 2019. Unlike SQLite, it's OLAP. That's why the queries are through vectorization and not the role-based. So it helps you come up with very complex queries, inquiries. And it has arrow. DuckDB has SQL interface. It can work with different data frames, pandas data frames, different other tables. It is compatible with Python. It has a high speed, it's a highly performing one, and it's an embedded one. I mentioned that previously. As for minuses, to use DuckDB, you need to come up with the preliminary processing of the big data and filter them. As well as that, you just need to analyze the code for its efficiency. Maybe you just need to rewrite the code for that purpose. In our team, most of the data mining utilizes SQL. I mean, data collection uses SQL interface, so we thought we'd use it. What did we end up with ultimately? So what did we put in production? With PyArrow dataset, I filtered the data and made projections preliminary. I read them from the memory. I would get the PyArrow table, and those PyArrow tables were joined together. After that, I had some volumes of data. I converted that to Polars. And after that, I moved it to classic pandas, where I continued my work as it is. So more detail about the first step. I would take PyArrow dataset, I filtered the data, made the projection. I didn't go beyond the allocated memory amount. So how did I do that? I took a piece of code, we import a data set with PyArrow, and then we send it to the path where the data lies, and we send it for partitioning. After that, we apply a filter. In this particular case, with the PyArrow compute, we say that we need to filter by the field where the value is more than 100, and then we come up with projection. We don't need the entire table here, actually. We only need to have column 1 and column 3. or two rather. So we end up with a PyArrow table on the second step. I joined those tables by the conditions I made it. So it looks like this: table 1, method join, we send it to table 2, keys, right keys, and type of join, like you can read on the slide. Here we read local benchmarks of memory reads were read in memory with pandas 16 seconds of time, read in memory Polars just 2.4 seconds, and PyArrow only took 1.4 seconds. Here we can see that the difference between PyArrow and Polars is very small, but the difference between Polars, PyArrow, and pandas is huge. The second step, I converted all those PyArrow tables to Polars, thanks to them using the same type of memory. I imported this to Polars, and we call from arrow and send the table there. We end up with Polars data frame. Then I had to fill up some of the columns with zeros, group something, regroup something, delete something. I did that with Polars. After that, I decided that okay, enough is enough, it's getting too complicated, and what's left is a small amount of data. And then I moved to pandas on my fourth step, where I did my final phase, final steps to split the data for the final test selection. Why we need that? Because if we learn the model at the test selection, there is a chance that the model will not learn to find the dependencies, it will just remember where it needs to come up with the right answers. So first of all, we teach the model, and then we test it so that it may look like a real industrial use, the real life use. What was the final result that I got? And I'd show you here. First, it's the resources, it's the time, and my solution. So I'll start with the resources. I had the CPU with 80 in the development, and only 10 in the production phase. I had 320 of RAM, and that was Apache, and the real thing was 80. The time was 2 hours, but in the production it was 3 hours. So it seems like that in the development I had 8 times more CPUs and 4 times more RAM in actual fact. Then we'll speak about the data volume. At the time the model was implemented, I thought that 6 months is not enough, so I decided to take 8. So the data volume actually increased by 33%. So therefore, my solution with the PyArrow Polars worked only for 1.75 times longer, although I had 8 times less CPU and 4 times less RAM. Seems like I managed to get a very good result, and the speed was not the thing that I was interested in, but that it worked smoothly and I had no out-of-memory scenarios at all. The distributed Spark did not come up by that point in time, so we discovered new opportunities of PyArrow and DuckDB. Further on, we had a task when we had to process a table which one partition was 450 gigabytes in size. So the data set had a get fragments mode, which would return certain data packages, and you can use these packages, and it worked. And the next phase was DuckDB. Our team also works with the third-party code. So once we got the model where data collection was for 500 strings of SQL code, so we thought it would be too long to rewrite that on our own. So we decided to apply DuckDB with a preliminary PyArrow and Polars filtration and work with partitions. And as we worked with partitions, we managed to change the source SQL code. It worked well, nothing crashed, and we were happy. What are the conclusions? Polars is a real powerful tool that should be used, if not instead of pandas, but together with it. Why? Because most of the operations, you may Google it, but most of the operations are done much faster in Polars than in pandas. And if you really need something like of a data scientist approach, you can come up with heavy operations in Polars, then you send it to pandas. It's done simply because they use the same memory. And I also conducted a local test. I had a Spark kit with data and I decided to read it with pandas. I don't remember how much time it took to read it with pandas, but then I decided to read it with Polars and make a transfer of Polars to pandas, and it took 5 or 6 times less time. So it's a real great solution. If you work with super big data, PyArrow is a very powerful tool to use. I recommend it to everyone. Of course, it needs some time to familiarize yourself with it. There's not a big community around it, but there are documents to read. If for you the SQL interface is a critical requirement, DuckDB is a great solution to use. We tried it, we liked it. This is it. Here I'm showing my contacts, my Telegram. If you would like to contact me, please send me questions.
Раз. О. Спасибо. Спасибо. Тебе насыпало очень классных вопросов.
Thank you. Lots of interesting questions for you. Just hold on, we'll start with simple ones. How come Polars, which is written on Rust, is slower than PyArrow? It's an interesting question, indeed. Honestly speaking, I don't really know why it so happened. I had local benchmarks, and the time it took for Polars was longer. Actually, PyArrow is written with the use C and ++. That's why. Can it be used for logs, the traffic dumps, so the cybersec targets? I actually didn't think about it as cybersec, but it's also data, isn't it? But I never even thought about it. There couldn't be anything. Everything is hidden. With all those logs that the system rejects in JSONs are data. Can you also analyze this data with PyArrow and Polars? I'm not sure about PyArrow. I think here we'll need to research it. I think you can do it with Polars. Did you have an experience with the R language, and did you compare it to reveal the higher speeds and higher performances? No, I never worked with the R language. Knowing that this solution will be supported by your colleagues, did you try to use Dusk, the distributed pandas, that one? Pandas version 2 can use Arrow, and it can accelerate the operations. I think you can try this. When I was studying this problem, I didn't Google any information about that, but I think it would be interesting to try. If you came up with a task today, would you stay on PyArrow I would have stayed on Spark.
что бы посоветовал?
What if you have dozens of terabytes of data? What would you recommend to do? I think it's worth inventing some kind of a parallel scheme. If I would do everything in one pod, I would be able to separate that. I would start Googling more efficient tools. Thank you.
Производили ли подсчет
Did
выгодности
you ever
компании?
calculate the
Обучение,
profitability?
были минус затраты на создание
Can you
и расходы на ресурсы.
compare the profitability
Кажется, да,
and
тут важнее впрод докатиться.
cost optimization? No, we didn't analyze such things.
Так, друзья,
So
из зала, возможно,
just to get it to production took a lot of money.
Привет, да.
Oh, we have a question from the floor from Dmitry. Can you hear me?
Раз. Да, спасибо большое.
Thank you.
Второй раз уже сегодня мы обсуждаем эту
Thanks again.
У меня
We discussed this topic for the second time today. I have three questions. First of all, I would like to go back to the slide where you'd show the benches of Spark versus PyArrow, if I remember that right. That you had on a single node and in a cluster. What was the performance of the Spark of the single node? I didn't have a spill. It was a local thing with big volumes of data, big amount of data, so I couldn't really pull it off. You need to give it a try. You need to give it a proper try. There was a part about lazy API and optimization. That was the part. That's the one, a lazy API in Polars. What kind of the optimizer does it use? Which data does it use? Can it rewrite simple rules? I did not study how it works under the bonnet, as you put it. I just verified that it works with such layout. So you may find more insights if you like. And finally, you said that Polaris is very powerful in its vectorization. Polaris is so vectorized and it's so good, but it was not about Polaris, it was about ProductDB. It was DuckDB. So what does DuckDB vectorize? What operations can be vectorized in DuckDB? Did you check this? No, I didn't drill this down so deep. For me, it was very important to roll this out and put it in production.
Вопрос из зала.